Chapter 1, Exercise 18. Note that this. Suppose that x is not the zero vector, and take any vector v such that v is not equal to ax for all a and r, and construct an appropriate vector y as a combination of the form v minus l for x. First, observe that if x equals a1, a2 to ak, y1 equals b1, b2 to bk, and y2 equals c1, c2 to ck, k element of natural numbers, then x dot with y1 plus alpha y2 ultimately equals x dot y1 plus alpha x dot y2. Let k be greater than or equal to 2. If x equals 0, then we can take any non-zero vector y in Rk, since x dot y ultimately equals 0. Let x not equal to 0, then x dot x does not equal 0. Let v not equal ax for all a and r, then we have this if and only if alpha equals x dot v all over x dot x. Thus, y equals v minus x dot v over x dot x times x satisfies x dot y equals 0. Considering the case k equals 1, if x equals 0, then y could be any real number. If x doesn't equal 0, then it's not true because the product of two non-zero real numbers is non-zero. So y would need to be 0, but that's not allowed. We'll say that w and v are orthogonal, perpendicular, if the angle between w and v is a right angle. In other words, the triangle with sides w, v, and w minus v satisfy the Pythagorean theorem, that is, this. And since this occurs if and only if w dot v equals 0. There are many ways to build y to satisfy the thesis of this exercise, and the following are some suggested reasons. 1. This is the initial procedure of the Gram-Schmidt orthogonalization process, an algorithm that allows one to build an orthogonal sequence from a sequence of linearly independent vectors. In the proof, if x and v are linearly independent, then x and v minus ax are orthogonal, like this and that. Then all vectors can be written as the sum of a multiple of x and an orthogonal vector to x. In addition, this sum is unique. 3. If x is an Rk is a non-zero vector, then H equals this, is a vector space. Indeed, note if v1, v2 in H and A is in real numbers, then we have this. Thus, A v1 plus v2 in H, and consequently, H is a vector space. The space H is called the hyperplane perpendicular to the vector w. The hyperplane perpendicular to the vector w through the point M is defined by this. Note, if k is greater than 1, then each hyperplane has infinite elements. When k equals 1, the hyperplane is reduced to a single point. If k is greater than 1, and x and y are 2 points in Rk, then the set of all points z, which are equidistant to x and y, that is, z satisfies absolute value x minus z equals absolute value y minus z, is the hyperplane perpendicular to the vector x minus y through m equals x plus y over 2, where m is the midpoint of the segment xy. Here's a picture. Geometrically, for k greater than or equal to 2, if x dot y equals 0, then x and y are perpendicular, x perp y. Given x and v are linearly independent in R2, we obtain y using y equals v minus x dot v over x dot x, x. Note the right angle between x and y. All vectors with the same direction of y are perpendicular to x. Here's a picture. Given x and v are linearly independent in R3, we obtain y using y equals v minus x dot v over x dot x, x. Note the right angle between x and y. All vectors with the same direction of y are perpendicular to x, and all vectors in the plane π are perpendicular to x. Thanks for watching.